Hello everyone. In this section, we're going to look more at the concept of process capability and also process performance. Our learning objectives are to understand the limits of CP and CPK when considering the process target. We also want to calculate process capability using a new index called CPM and compare CPM to CP and CPK. We want to understand the concept of long-term versus short-term variation and calculate the process performance indices PP and PPK. So just recapping, of course, we're looking at normally distributed random variables. We can model then our population of a normally distributed variable with a mean mu and a standard deviation to represent the variability of our population. When we look at this population model with respect to specification limits, our lower spec limit and our upper spec limit, we can then come up with the idea of capability. So here we're assuming that our process mean is equal to the target, which is the midpoint between the upper spec limit and the lower spec limit. And a process that produces all of its units within the specification is said to be capable. And here we made use of capability indices. These provide us numerical measures of quantifying the capability of a process. And the most common were, of course, CP and CPK. So CP, again, is defined as the variability allowed in the specification divided by the variability present in the process. So upper spec limit minus lower spec limit over 6 sigma. And sigma is the standard deviation of our process. So we're comparing the variability from a normal distribution to the variability allowed in the specifications. And if CP is equal to 1, that means almost all of your output falls within specification, actually 99.73%. If the value is less than 1, then the process variability is larger than the variability allowed by the specifications, and so you're producing rejects. So general CP that's bigger than 1 is good. Now, CPK helps us out because CPK not only looks at the variability, but also looks at where we're centered. Are we actually centered right in the middle of our specifications, or is our distribution moving from one side to another and falling out of specification? So we said CPK was more powerful than CP, but what is missing from both of these two capability indices? How many of you have already figured it out? What is missing here? Our CP and CPK indices do not include the target. We assumed that the target was equal to the process centering, and that is at the midpoint of these two specification limits. But let's say that's not true. That is not the target. This is our process mean, but let's say our target is somewhere else. T for target. Then CP and CPK do not tell us anything about the target. They're only focusing on the variability of the population with respect to the specification limits. So for this, we have an index called CPM. This was first proposed by Chen, Cheng, and Spiring in 1988. It's defined as the upper spec limit minus the lower spec limit over 6 sigma prime, where sigma prime, this little prime mark there, is equal to the square root of the sum of the squared differences of every individual x value from the target value divided by n, where n is the number of measurements. So the CPM value takes into the account the sigma, it takes into account the target. Now let's look at what this means. So here again is the CPM definition here. Now what you see here on this side is sigma, our population standard deviation, is measuring the variability of the individual values. So here's our individual values all different, we're modeling them, of course, and we're measuring these, this is a little bit off this picture, we're measuring this sigma value from the process center. On the other hand, this sigma prime, our new variable, is measuring the variability of our data. So our data's in a kind of a bell shape. Here's our target. This time we're measuring this variability, taking that into account. Now, how do you do that? You apply then this equation here, which includes the target. It's measuring the difference, the squared difference of every individual value from the target. So the major advantage then for this CPM index is it considers the target not just the usual two-sided tolerance limits. Now, these tolerance limits, by the way, people like football, LSL and USL, these sort of goalpost limits, they're called. You know, you're trying to hit the football, American football, right through the center of the goalposts. These imply that outside of the limits you have loss, but there's no loss as long as you're within the limits. Now, we looked very briefly, and we don't do much in this course on this, but we looked very briefly at the Taguchi loss function in one of the earlier lectures. And this says that the loss is only going to be zero when your characteristic is exactly on target. And the loss will increase quadratically when the value moves away from the target. So using this CPM index follows this loss function philosophy, and maximizing the value of CPM amounts to minimizing the loss function. So maximizing the CPM is when you're on target. If we rearrange our equations, we can write CPM as CP over 1 plus V squared, where V is equal to T minus mu over sigma. And again, mu and sigma are back to the process standard deviations that we've used before. And now it's just a matter of using our new equations to calculate CPM. So let's do an example. Let's calculate the CPM for the process with the following data. USL is 30, LSL is 10, and the target is T equal 20. So actually in this example, the target is falling right between the USL and the LSL. Process mean is 22, and the process sigma is 3. So first of all, CP is equal to USL minus LSL over 6 sigma is equal to 30 minus 10 over 6 times 3 is equal to 20 over 18 is equal to 1.11. CPK, might as well do this as well, is equal to the minimum of the USL minus the process mean over 3 sigma, or the mean minus the LSL over 3 sigma. And so that's equal to the minimum of the 30 minus 22 over 3 times 3, or 22 minus 10, 3 times 3 is equal to the minimum of 8 over 9, or 12 over 9, everyone following this, is equal to 0.889. CPM now. Okay, so CPM was equal to CP over the square root of 1 plus V squared. So V is equal to T minus mu over sigma is equal to 20 minus 22 over 3. So we have basically minus 2/3 there, but we're squaring it. So 1.11 square root of 1 plus, that will drop out the minus. And if you work that all out, you're going to get 0.923. So looking at all these different values, what we see is that the CP here is greater than 1. So our process is, if you consider greater than 1 capable, it's capable. Most of the data is falling within the upper and lower specification limits. Good. very nicely, you know that even if you're off center, if you were on center, you could fit within the specifications. Now we do know we are off center here, and so you do see that the CPK value is less than 1. This means there is a percentage that is falling out of specification. In this case, we're falling closer to the upper spec limit because our mean's at 22. Still pretty good though, 0.889, but could be better. CPM, now this is just this example. In this example, the CPM falls actually in between these. But what you see is both CPK and CPM are less than CP. They are both taking into account this off-centering. And CPM in this example is bigger than CPK because it is actually looking at, again, the target. It's considering the target. And since this mean is actually not so far from target, you get a slightly higher value. But let's look at some more examples here. So comparison of these indices. If the process is centered, then CP equals CPK is equal to CPM. So this is, oh, excuse me. Let's in this example, what I'm assuming here is that you have LSL, USL, and this midpoint here is the target, is at the midpoint. So for the first example, if maybe I can change the color. If you have this centering, everything is centered. Not very centered, does it? If it's centered, then CP equals CPK equals CPM. However, if the process is not centered, then CPM and CPK will be different from CP, and they'll both be smaller because, again, as we said, CPK and CPM both evaluate the lack of centering of the process in addition to the variability, although they follow different approaches. Now, another thing to note is CPM will never be negative, whereas CPK can actually assume CPK can be negative if the process center is actually outside the specification limits. Then you can have a CPK equal to be negative. CPK and CP, as we said before, are assuming the target is at the center of the specifications. And of course, this is more critical than for the CPK. You're calculating it from the specification limits, implying that, with the implied assumption that the target is at the center. On the other hand, the calculation of CPM does not use the specification limits, but instead uses a specified value for the target. So if the target is at the center of the specifications, like we're showed here, then CPK and CPM are comparable. Both indices will decrease in value when the process variability increases or when the process mean gets away from the target. But if the target is not at the center of the specification, then CPK and CPM behave very differently. So let's compare these. Here's an example, assuming this example is from this reference here. Here we are assuming the two-sided specification with the target at the center of the specification. So LSL, USL with the target right in the center. Now, looking at process A, where the process mean here, mean is equal to the target. So target is at 50, the mean is at 50, given a standard deviation there. CP equals CPK equals CPM. In process B and C, however, now we've got a smaller, see the standard deviation here was 5, here we have a standard deviation that's less. In both of these, the CP value increases. Look, here's a CP of 2, here's a CP of 4, so very good, right? Because you see a reduction in the variability. But the values of CP and CPM are smaller compared to CP because of the lack of centering in the process. Here CPK is 1, CPM 0.63, K1, CPM 0.44. Now, value of CPM is smaller than CPK in both processes B and C, which is reflecting the fact that the CPM reacts more sharply than the CPK when the process moves away from the target. And notice also, while CPK value here equals 1, look at this, for process B and D for process C, here we have this reflects that almost all the units of the population are actually within the specification. The aspect of the CPM index is concerned more with the location of the process with respect to the target. More with the location of the process with respect to the target, rather than reflecting on how well the units of the population meet the specification. This is what makes it different. So really, it boils down to, if the purpose of using your index is to see how well the process produces a characteristic within the specifications that the customer's given you, then you probably don't need your CPM. CP and CPK, or CPK is enough. However, if you're interested in looking at how well you're meeting the target and you want to reflect the losses that could be happening due to the process moving away from the target, then you should use CPM to give you a better estimate of the process's performance.